Hey guys, so tonight we're just going to recap what we've learned the last couple days regarding momentum and regarding impulse. And so first we're going to start with momentum. And if you remember, momentum actually has two definitions. So if you'll remember, the first definition of momentum is that it's the product of the mass and the velocity of an object. Or in layman's terms, we could talk about how difficult it is to stop a moving object. So if you think about an object with a lot of momentum, it'd be a very large object that's moving very fast. Let's say, for example, a speeding locomotive would have a lot of momentum, which would mean it's very, very difficult to stop. If you have a very small object that's not moving very fast, it would have very little momentum, and therefore it'd be very easy to stop. So we've talked about our verbal definitions here, but we also have a mathematical definition of momentum. All right, so the mathematical definition is that P equals m times v. So just like we said above, the product of the mass and the velocity of an object is equal to the momentum. So m stands for mass measured in kilograms. We've seen that many times before. V stands for velocity in meters per second. We've seen that one many times before. And our new variable here is the P for momentum. And I know it's weird that P stands for momentum. It actually comes from the Latin word impetus. But we use P for momentum, and that can be measured in kilogram meters per second or newtons times seconds. Now in this situation, it makes more sense to use kilograms times meters per second, because that's what you get when you multiply mass times velocity. Also notice that we have arrows over the P and the V, and if you remember, that stands for a vector, meaning that they can be positive or negative depending on the direction of the momentum and the velocity. If something was moving to the right, we would typically say it has a positive velocity and momentum. If something was moving to the left, we would typically say that it has a negative velocity and momentum. So let's try an example problem. Alright, so in this simple problem, we have a car with a mass of 1,200 kilograms, and then we're told it's moving to the right with a speed of 24 meters per second. We want to know what is its momentum. So the first thing we're going to do is label our givens and our unknown. Alright, so as we can see here, we've labeled our mass as 1,200 kilograms. We've labeled our velocity as positive 24 meters per second because it's going to the right. And we have labeled P as our unknown because we're solving for the momentum. Next thing we'll want to do is write our equation and rearrange it for the unknown. So I've written the equation P equals m times v. I actually don't need to rearrange here because it's already solved for P, and that's what we want to know. So the next thing we can do is just plug in our numbers. So P is equal to 1,200 times 24, and then we can simply solve that and put our units. So that is 28,800 kilograms times meters per second. And we can go back and remember our arrows here, and that will be a positive number because once again it's to the right. Alright, so the other thing we got into with our activity was impulse. And so if you remember, impulse is the product of the force applied to an object and the time over which it's applied. Or another way to say that is that it's the area under the curve of a force versus time graph. Now when we're applying a force over time, there's kind of two things that could happen. It can be a variable force, or it could be a constant force, and we're going to look at both of those. Alright, so on the left I have a sketch of a variable force versus time. This is actually very similar to the shape you got in the lab that we did. And so as we can see, we start with zero force, and then that force gradually increases to some maximum, and then goes back down to zero over time. And so if we wanted the impulse from this graph, the impulse would actually be this entire area underneath this peak here. And to calculate that, you can either use a fancy computer program like we did for the lab, or you can use calculus. So neither of those would necessarily be things you'd have to do on a test, but we do use some labs where we have computers calculate that area for us. Now let's look what a constant force versus time would look like. So for the second graph here on the right, we can see it's simpler. We have a force that is constant applied over a certain amount of time that we see from here to here, t. And then once again, the impulse is going to be the area under this curve, but the area under this curve happens to be a rectangle. And as we all know, the area of a rectangle is just the length times the width. So if we want to calculate our impulse here, it's just going to equal our force times our time. So that gives us a mathematical equation definition for impulse as well. All right, so J equals F times T. So F stands for force, and as you all know, that's measured in newtons. T stands for time, and as you all know, that is measured in seconds. J is the symbol we use for impulse for some reason. I have no idea why. And it can be measured in Newton seconds, which really makes more sense because you're doing newtons times seconds for force times time. Or it can also be measured in kilogram meters per second. And hopefully it's sticking out to you that the units for impulse and the units for momentum are the same, and that's going to become very important, and you may already know why from the activity that we did. Once again, F and J have the arrows over showing that those are vectors, and they may be positive or negative depending on their direction. Alright, so once again we have an example problem. Let's say a man pushes a car with a force of 200 newtons to the right, and he does that for 10 seconds. And we want to know what is the impulse the man delivers to the car. So once again, we're going to label our givens and our unknown. So as we see here, we've written down that we have a force of 200 newtons. It's to the right, so we'll leave it positive. It was applied for a time of 10 seconds, and we are looking for our impulse. So now we can write the equation and rearrange if necessary. And as we can see, it's already solved for J, so we don't need to rearrange our equation, so we can just substitute in and solve. So J equals 200 times 10, which would be 2,000 Newton seconds. And once again, I've left that as a positive number because the force and the impulse would both be to the right. Alright, so the final thing we're going to talk about is the impulse momentum theorem. So as you all presented me in your labs, when you graphed impulse versus change in velocity, you get a straight line with a positive slope and a y-intercept of 0, as we've shown here, showing that your impulse and your change in velocity are directly related. Secondly, you all noticed that your slope was pretty much equal to the mass of the cart that you used in the lab. So let's compare that result with our y-intercept equation for a line. So y equals mx plus b. Now, for this lab, we saw that we had a y-intercept of 0, so we can get rid of that term there. And then let's start replacing. So on the y-axis, you guys graphed your impulse. The slope, as we said, was the mass, which is also m. M stands for slope, but m also stands for mass. And then on the x-axis, we graphed our change in velocity. Now, if I distribute that mass through those parentheses, what I'll see here is m times vf minus m times vi. Now, what this really is the impulse momentum theorem, because what we've figured out here is that J, which stands for impulse, is equal to the final momentum, m times final velocity, minus the initial momentum. So what we've really figured out then is that the impulse on an object is always equal to its change in momentum. And you guys proved that through the lab that you completed. And we're just recapping it tonight. So I've got a few problems for you guys to try attached to this Google form. Please submit those tonight. We will go over them at the beginning of class tomorrow, make sure we correct any mistakes you may have made, and then we'll try some more problems related to impulse, momentum, and the impulse momentum theorem. See you tomorrow.